In this video, I want to go over some of the post-lab calculations and the sources of error in the experiment that we did with the atomic mass of aluminum. I'm going to be using the data that is in that experimental video, though you will have different numbers if you perform the experiment in class. And just to review, some of the data that was collected, you would have massed this piece of aluminum. You would add excess HCl for molar HCl, and then a reaction would occur. It would produce hydrogen gas, which would be then going through this tube and bubbled into a container that is completely devoid of any type of air or gas to start with. And then H2 gas would bubble in here. Since it's being collected over water, not only would you have H2 gas, but hydrogen gas, but you would also have water vapor. So you would end up having a mixture of both of those two substances collected in this tube. And then once the reaction stops, there's volume measurements over here. You can get both the volume of the gas. You can equalize the water levels inside and outside so that you can say the pressure inside would be the same as the pressure in the room, or atmospheric pressure, which you can measure with the barometer and record that. And then you can measure the temperature. So you would end up having volume, pressure, and temperature, which is enough information to get moles of the gas collected using PVNRT or PIVNR. So just going through those calculations quickly. I've rewritten them here to save time. Remember, we want to isolate the pressure of just the hydrogen gas, since both hydrogen gas and water is collected in that tube. So we're taking the total pressure, which is just the atmospheric pressure we measure with the barometer, and subtracting out the partial pressure of H2O, which is just the water vapor pressure at that temperature. And you can get that from your lab by scrolling down. Okay, it was about 23 degrees in the experiment that you saw in the video, so it's about 2.8 kPa, but we've got to change that to be the same units, because when we add or subtract, we need to be in the same units. And then you can subtract, and this is the hydrogen gas partial pressure. That I could write millimeters of mercury, or torr would be the same exact value here. Then I can plug into PVNRT and rearrange to solve for moles of H2, but make sure you're plugging in the partial pressure of H2. You had to have subtracted out the water vapor. Whenever you're collecting over water, you have to subtract out the water vapor pressure. This is the volume of gas that was collected. Here is my R value in torr, so that torrs cancel. Remember, volume has to be in liters to use this R value. And my temperature has to be converted to Kelvin. And then when I plug into PVNRT, I get 6.52 times 10 to the negative fourth moles of H2 was collected. That's what was actually produced in my experiment with the pressure, volume, and temperature that I recorded. I can then use stoichiometry to change this moles of H2 into moles of aluminum if I have my balanced chemical reaction. You'll find it's 2 moles H2, or 2 moles of aluminum are used up to produce 3 moles of H2. And then I'll see that 4.35 times 10 to the negative 4 moles of Al is what reacted. I can then figure out the molar mass of aluminum because I have grams and moles of the same substance, the same starting sample essentially. This was the grams I measured out in the lab, and this is the moles I've calculated through stoichiometry, and I get 29.9 grams per mole with this data, which is pretty close to the about 27 grams per mole that's in the periodic table, though there is some sources of error in here. So now we kind of have to figure out, okay, what could have caused this error? Notice my molar mass is higher than I anticipated, than I expected. So we're going to think about sources of error that would have caused this to be too high. Anything that would cause it to be too low would not be a valid source of error for this particular experiment. And sometimes on the AP, they're asking you about molar mass. Sometimes they would have just been, hey, how does it affect your moles? Sometimes, and you'll see later, there's a calculation with percent yield. Well, how would this have affected percent yield? So you really have to follow through your calculations and see what effect each of these things would have. So I'm just going to go through a few of them here. There's a whole section here. So if some hydrogen gas escaped from the syringe, would your calculated atomic mass be too high, too low, or the same? Fully explain. So let's think about what this would impact in my calculation. So the pressure that I would have calculated would be the same because I'm getting that from the barometer on the wall. Right? The temperature I recorded would be the same. I'm getting that from my thermometer. What would be impacted is the volume of gas. So if some of it leaked out, I actually should be having a higher volume than what was actually measured because some of the gas isn't being accounted for in that gas collection tube. So if the volume were higher, let's see how that would impact this. If the volume was higher, okay, then the moles of H2 collected would be higher. Okay, if the moles of H2 collected would be higher, if I trace through, then that means also the moles of Al would be higher. And that's in the denominator of my molar mass equation. So if that were higher, that would, since it's in the denominator, I'm dividing by it, that would cause my molar mass to be lower. So I should actually have gotten a lower molar mass, which might have been closer to the accepted. I want a lower molar mass. My molar mass for this experiment was too high. So that is a valid source of error. And again, the impact would be that the calculated one is too high. Had I plugged in the correct volume, if I had plugged in a higher volume because some of that gas is missing, I would in fact have gotten a lower molar mass. So as it stands now, since that's kind of what this question's wording, as it stands right now, my calculated atomic mass, this is too high. It should have been lower. Let's take a look at another one. These two are talking about water levels. Now, water level is going to translate to pressure. So just kind of looking at, I have it over here. Just kind of looking at this diagram here, I want to talk about water levels for a moment. So the whole idea is that we want the water level in here and the water level outside to be the same, so that the pressure of the atmosphere that's pressing on the outside is going to be the same as the pressure of the gas inside, because we are measuring the pressure of the atmosphere in the lab, and we want to say, hey, that's the same as what's inside. Now, what's going to happen if these levels are not the same? So the first one says, okay, the water level inside the syringe was lower. So if, in fact, the water level inside were lower, okay, it would look something like this, right? So let's say this is the outside container and inside is lower. That means the pressure of the gas inside and the pressure of the atmosphere are not the same. The gas, if you notice, is actually pressing harder. So the pressure of the gas is actually higher than what I'm recording in the lab. If the pressure inside is actually larger than the atmospheric pressure, if you're using the atmospheric pressure as your total pressure of the mixture, you're actually underestimating your pressure of H2. This value is actually too low. It should be higher if the pressure inside is higher than atmospheric pressure. So then if I look at my calculation, this number is too low. Okay, in fact, it would be higher because my pressure is in the numerator. And if I were to track through to my moles of Al, then this number would be too low. Okay, and if I were to then see, okay, this is in the denominator, if this is too low, then, oh, then this number is too high. That could be a valid source of error. Had I actually plugged in a higher pressure, which would create higher moles, and then that would go into my denominator, I would have gotten a lower molar mass closer to my expected. So that's actually a valid source of error. My calculated is too high. So notice that I kind of just walked through conceptually these two ones a little differently. There's more than one way to explain your answer, and I've looked at my calculations before I've settled on too high or too low. I kind of start talking myself through the problem first. But you can say, okay, what effect would plugging in this higher number, or you could figure out, oh, I've underestimated something. What effect would that have? So there, like I said, there's more than one way to really explain what's happening, but just notice all I'm doing is I'm finding what number would be affected and really following through my calculations and seeing what effect that has on my final calculation. Obviously, the water levels being reversed would have the opposite effect. The next source of error talks about temperature. So if the temperature was actually higher than what you recorded, so here's where temperature is. So if the temperature is higher than what you've recorded, a higher temperature, since it's in the denominator, would result in a lower moles. Okay, a lower moles of H2 collected would mean a lower moles of Al had reacted, and that would be a lower number in my denominator. And then if I'm dividing by a lower number, that would mean my molar mass would have been increased had I used that higher temperature. Or if I want to use a different line of thinking for the same question, if it were at actually a higher temperature, this value is too low. So if I'm dividing by a number that's too low, that means that this value as it stands is too high, which means that this would be too high. And if this is too high, in my denominator and I divide by a number that's too high, that means that this number is too low. It's lower than it would have been had I plugged in my actual temperature. So notice that this is not either way that I'm tracing this source of error through. If I want to talk about what the wrong number effect is, or if I want to talk about what plugging in the other number effect would have had, either of these would not be a good source, whichever way I'm looking at it, wouldn't be a good source of error for this experiment, because this number is not too low, it's actually too high. The reverse, the temperature having the temperature is lower than was actually recorded, then that could be a valid source of error for this experiment. And you might say, okay, temperature would also affect the vapor pressure of water, because the water vapor pressure depends on temperature as well. So if you wanted to talk about that aspect, you can as well. It is going to not have as large of an effect in the sense that if you look at your temperature here, it does change very slightly, but it does change. So that is something else you could trace through. I'm just purely looking at temperature here. If your aluminum did not fully react, and you can look at this in different ways in the experiment, but one way you could look at it is saying that, well, this number is not fully reacted. That doesn't represent the sample that fully reacted. This number is going to be essentially too high, so that would make your molar mass too high. So the molar mass, in fact, should be lower, and that could be a source of error in this experiment. The last source of error talked about is the HCl solution's 5 molar instead of 4 molar. Well, HCl is the excess reactant, so by adding more of it, because a higher molarity would have higher moles, would not change anything here, in the sense that it was already in excess. So adding more moles is not going to do anything. They're just going to be left in the container. So your atomic mass should be the same, perhaps unless your aluminum didn't fully react, or in fact it wasn't in excess to start with. So notice that you should just be able to really track through these different sources of error. And I'm talking here, since it asked about molar mass, I was looking at the effects on molar mass, but you might be asked for the effects on anything. They might just say, well, how would that affect your moles of H2 gas? Like I said, there was an equation with percent yield. First of all, make sure you know the difference between percent yield and percent error. They're two different equations, but percent yield is the actual over the theoretical times 100. So what effect would these things have on the percent yield? Is it affecting the actual, which was calculated here with PV-nRT? Is it affecting the theoretical, which you would get, how much you would theoretically get by reacting all this 0.013? What's being affected and following through your calculations?